Just look around you for a second. That car zipping down the road, a cricket ball flying for a six, even you just sitting there watching this. It's all motion, right? But have you ever wondered, what are the invisible rules that control every single one of these movements? Well, today, we're going to pull back the curtain and find out.
Come on, you know the feeling. You're just standing in the bus, maybe listening to some music, everything's fine, and then the driver slams on the brakes, and what happens? Whoa! You suddenly lurch forward, don't you?
And what about the other way around? The bus is stopped, and then suddenly it jumps forward. You stumble back, trying to catch your balance. So what's going on? Are we all just a bit clumsy? No way. These everyday feelings, this push and pull, they're actually clues, little messages from the universe that point to some of its biggest, most important rules.
All right, so to figure out these mysteries of the bus, we have to start with the most basic thing in all of physics, the one thing that makes anything happen at all. It's an invisible push or a pull that we call force. So what is a force, really? Well, you can think of it as the universe's change maker. Imagine a book on a table. It's just going to sit there forever, unless a force comes along to move it. And if a ball is rolling, it's going to keep rolling forever, unless a force stops it, or speeds it up, or turns it. Simply put, force is the reason why anything ever changes what it's doing.
And you know what? At the end of the day, every force, no matter how complicated it seems, is really just one of two things. It's either a push or a pull. That's it. Pushing a shopping cart at the supermarket, that's a push. Kicking a football, also a push. Pulling your heavy school bag, that's a pull. Fetching water from a well, yep, that's a pull too. See? Simple. Okay, so what exactly is a force capable of? What can it actually do? Well, you see the effects all around you. A force can start something moving, like when you kick a football. It can stop something from moving, like when a wicketkeeper's gloves catch a super fast ball. It can change the direction. Think of a batsman hitting that ball towards the boundary. And get this, it can even change an object's shape. Like the dough for making chapatis, your hands are applying a force that completely changes its shape.
This all leads us straight to the first great rule from the man himself, Sir Isaac Newton. Now, this isn't the official name, but I like to call it the law of laziness. And trust me, it's a brilliant way to remember it. Basically, objects in the universe are a little bit lazy. They just want to keep on doing whatever it is they're already doing.
Okay, here's the official definition, the one you'll want to remember for your exams. It says a body will stay put if it's resting or keep moving steadily in a straight line, unless an external, unbalanced force comes and messes things up. Now that word, unbalanced, is super important. It just means a force that's actually making a difference, one that isn't being canceled out by another force.
So this laziness, this natural habit of objects to resist any change in their motion, it has a proper scientific name. It's called inertia. It's the property of an object that makes it say, nope, I'm comfortable doing what I'm doing and I don't want to change.
And believe it or not, inertia is what solves our mystery from the beginning. Let's break it down. When you're standing still in that train, your whole body has inertia of rest. It wants to stay still. Suddenly, the train lurches forward. Your feet, since they're touching the floor, go with the train. But your upper body? Thanks to inertia, it resists. It tries to stay right where it was. The result? Your feet zip forward from under you and you feel like you've been thrown backwards. And boom, mystery solved.
Now, here's a really important point. Inertia is all about mass. It's a simple rule. The more mass an object has, the more inertia it has, meaning the more it resists change. It's exactly why pushing a fully loaded shopping trolley is so much harder than pushing an empty one. The loaded trolley has more mass, so it has way more inertia. It really doesn't want to start moving.
Okay, so the first law tells us what happens when there's no force or when all the forces cancel each other out. But what happens when there is an unbalanced force? What then? For that, we need Newton's second law. This is the big one. This is where we go from just talking about motion to actually calculating it.
Right, now the official definition can sound a bit scary. It's talking about rate of change of momentum and all that. But don't worry about the jargon. We can boil this all down to one really powerful idea that connects how hard you push something, how heavy it is, and how fast it speeds up.
Let's just break it down into simple, common sense ideas. First, the harder you push something, the faster it's going to speed up. More force means more acceleration. Makes sense, right? And second, if you have two objects and one is much heavier, you're going to need a lot more force to get it to speed up at the same rate as the lighter one.
And those two simple ideas are captured perfectly in one of the most famous, most powerful equations in the history of science. Force equals mass times acceleration. F equals ma. Just 3 little letters, but they are the absolute heart of physics. This isn't just some formula for an exam. This is the rulebook for how everything in our universe moves.
Now, here's something really cool. You might think these laws are 3 separate things, but they're actually beautifully connected. In fact, the first law is secretly hiding inside the second law. It's like a special bonus feature. Let me show you.
Okay, let's look at our big formula again. F equals ma. Now, just for a second, let's imagine a situation where there's no outside force acting on something at all. So what would that mean for our formula? It would mean that F is equal to 0.
Right? So if F is 0, and we know our object has some mass, then for the math to work, the acceleration, a, must also be 0. And what does 0 acceleration actually mean? It means no change in speed or direction. The object's motion doesn't change one bit. If it was still, it stays still. If it was moving, it keeps moving at the same speed. And what does that sound like? That's Newton's first law. See? It was hidden inside the second one the whole time.
And that brings us to the grand finale, our third and final law. This is a law that controls every single interaction in the universe, from you just tapping your finger on a screen to 2 galaxies colliding. It's Newton's third law, the law of action and reaction.
You've definitely heard this phrase before. It's one of the most famous lines in all of science. It's so simple, so elegant, and it's always true. Every single time a force is applied, the action, another force instantly appears, a force that's just as strong but points in the exact opposite direction. The easiest way to think about it is this. You can't touch anything without it touching you back. If you go and push on a wall, that's your action. The wall instantly pushes back on your hand with the exact same amount of force. That's the reaction. And yeah, that's why it hurts if you push too hard. And if you want to see the most spectacular example of this law, look no further than a rocket launch. The rocket's powerful engines blast hot gases downwards with an unbelievable amount of force. That's the action. Now, the third law says the gases have to push back, so they exert an equal and opposite force upwards on the rocket. That's the reaction. And that simple reaction force is powerful enough to lift a massive machine off the ground and send people to the stars. Amazing, right?
So what have we really learned today? Well, from the simple act of you walking, where your foot pushes the ground backward, that's action, and the ground pushes you forward, that's reaction, all the way to launching spaceships. These 3 simple laws are not just some boring rules in a textbook. They are literally the invisible blueprint of our world, shaping every single thing that happens.
So what's the most important thing to take away from all this? It's that these laws are not just history lessons. They are the operating system of our universe. From that laziness of inertia that keeps you glued to your seat, to the F equals ma that decides how fast a cricket ball flies, to the action-reaction that lets us walk and even fly, Newton basically gave us the language to understand the world. So next time you see something move, remember, the universe is talking to you in the language of physics. The only question is, are you listening?